Electron configuration part 2. In electron configuration, once we understand the means and the order by which electrons will occupy orbitals, we have to be able to represent this configuration in some way. We use diagrams generally to represent electron configuration. These diagrams are referred to as orbital notation. They consist of means by which we represent electrons with arrows. And if we look at orbitals that are filled, as we discussed, orbitals are generally filled according to their particular energies. So in general, we'll have a 1s orbital, then a 2s orbital, then a 2p orbital, then a 3s orbital, so on and so forth. If we have, for example, the element aluminum, aluminum consists of 13 electrons. Filling up electrons in these orbitals, then, we have the 1s, the 2s, the 2p, the 3s, the 3p, in order, as we see above. We fill each orbital with 2 electrons. The 1s orbital has 2, the 2s orbital has 2. The three 2p orbitals have 2 each. The 3s orbital has 2, and the only remaining electron at this point then goes into one of the 3p orbitals. There are 3 different types of orbital notation which we examine. There are what we call standard orbital notations, which is similar to what we just saw above. There is what's referred to as a condensed orbital notation, and there is a simplified orbital notation. Standard orbital notation uses arrows to represent electrons. There are either spin-up electrons or spin-down electrons, which are represented respectively by arrows pointing up and arrows pointing down. We use either boxes or blanks to represent the orbitals in which these electrons are configured. So if we have, for example, an atom that has a total of 10 electrons, we would have here the 1s, the 2s, and the 2p, each occupied with 2 electrons each, one spin up, one spin down. These can be represented either with blanks, as you see, or with boxes. A standard orbital notation will show all electrons in an atom in this configuration. This is also referred to as an orbital diagram. Now, condensed orbital notation functions generally in the same way as a standard orbital notation, where we have arrows that represent electrons that are spin up or spin down electrons, and using boxes or blanks, just like we did before. However, not all the electrons in a condensed orbital notation will be shown. All the inner shell, or what we call core electrons, are represented using the elemental symbol for the noble gas inside of a bracket. So if I look at an element like the one above, where I have 10 electrons, the first noble gas in the periodic table is helium, which has 2. The electron configuration for helium is a 1s with 2 electrons in it. So I would put the electrons from the noble gas inside the bracket, or represent them using the bracketed elemental symbol, and the remaining electrons are drawn out as normal. So for this above example, the 1s electrons would be represented using the helium core, and then the 2s and 2p electrons are represented in the same fashion as they have been previously, using arrows up and down, either with blanks or with boxes. Simplified orbital notation takes either a condensed orbital notation or a standard orbital notation and simplifies it down by eliminating the use of the arrows. We can write the orbitals in the same order, and we use a superscript numerically to represent the number of electrons in each orbital. So for the previous example that we were looking at that had the 1s, the 2s, and the 2p, there were 2 electrons in each of the s orbitals and 6 in the p orbital. So we would represent that configuration as a 1s with 2 electrons, a 2s with 2 electrons, and a 2p with 6 electrons. So you see how it compares to the standard orbital notation that we drew earlier. Now, valence electrons are the most important electrons within an atom, and electron configuration generally allows us to examine the electrons which are valence in an atom. Valence electrons are those electrons which are free to make bonds, either ionic bonds or covalent bonds. Generally, valence electrons are the highest in-value electrons, although this is not always the case. So for example, if I had an atom with an electron configuration of 1s with 2, 2s2, and 2p5, the highest in-value in this atom that is occupied is n equals 2. If I look at all of the orbitals that have an in-value of 2, there are the 2s orbital, which has 2 electrons, and the 2p orbital, which has 5 electrons. So the total number of electrons in the highest in value is 7. So there are 7 valence electrons in this particular atom. Now the highest n value are not always the only valence electrons in an element. For example, if I have d transition elements, the d level is often free to bond as well as the p and the s orbitals that are in the higher n values. If I look, for instance, at cobalt, cobalt has the condensed electron configuration of the argon core, 4s2, and a 3d7. If I were to make this a 3+ cation, cobalt 3+, I would remove 3 electrons, so I would take away the 4s2 and one of the 3ds, which would leave the argon core and 3d6. If I'm given a choice in the particular configuration of the element, we would always take the highest s and p orbitals before we start to pull from d orbitals. So for example, if I go from cobalt to cobalt 2+ instead of 3+, I would take the 2s electrons before I would begin to take the 3d electrons. So the final configuration for the cobalt 2+ would be argon core with 3d7, not the argon core with 4s2, 3d5.